In my narrowband workflows, I like to take my mono images nonlinear before combining them into a color SHO image. Since each narrowband image can look very different one from another, I'd like to be able to do what processing makes sense to me on each individual image before I do the combination. My basic process is to take the images nonlinear, and then I go starless. At this point, I may or may not do some processing, but then I want to combine the images using the channel combination tool to create my initial SHO color image. I then process this, and finally I will add the stars back in to get the final image. But how do I make sure that the channels are balanced before they're combined so I get the best colors from the image? I sometimes do this by eye. I use the curves tool and the histogram tool to adjust each image and compare them and get something that I think looks like the right balance. Other times, when I want to be more precise, I use the LinearFit process to balance the images before combination. As an example, I'm going to use a recent image that I reprocessed of SH2-101, the Tulip Nebula. This is the final image I ended up with, but let's look at what the images look like early on in the processing steps. What I'm showing here is my hydrogen alpha, my oxygen 3, and my sulfur 2 images just after I've gone starless. Now I want to combine these images, and before doing that, I want to balance them so I get the best color possible. Typically, we have a really strong signal with the hydrogen alpha, which we do here. In this case, we also have a pretty good signal with the sulfur 2 image, but the oxygen 3 is pretty muted here. This is the one that has the weakest signal. So I'm going to try to balance these images using the LinearFit tool. You look under Process, scroll down to Linear. There's LinearFit. And here is the LinearFit tool. The LinearFit tool only has a few controls on it. It has a reference image, and it has a reject low and a reject high threshold. What LinearFit's going to do is it's going to take one image as the reference image, and it's going to compare all the pixels of its image to another image, create a LinearFit equation, and use that equation to transform the other image so that the D-min or the background sky and the contrast is more similar to the reference image. Now, I've read various guidances on how to choose your reference image. Some guidance tells me to use the image with the strongest signal. In this case, it would be the hydrogen alpha, and use that as the reference image. And then when it's applied to the other images, it will scale those images up to match. In my experience, I haven't liked the results I've gotten when I do that. When you have a very weak signal, like we see here in oxygen 3, there's a lot of upscaling that ends up happening to bring it up to the same levels as the hydrogen alpha. And I find that it looks noisy, there are artifacts, noise artifacts, and I'm not very pleased with the final image. On the other hand, I've also seen guidance that suggests you should be taking the weakest signal. Use that as your reference and bring everything down to its level. That's not a bad idea. All you're really doing is taking these strong signal images and you're compressing them down so they compare better to the reference image, but all the data and information is still there. It's just been scaled so it's more appropriate when compared with the lower signal images. So why don't we try that? We're going to take the oxygen 3 image and we're going to use that as our reference image. Bring that down, drop it here, and we now have that. Now we have other parameters that we can set. Now, as I said, this is really doing a linear fit. And when you compare two images like that, for the most part, things are linear, but there are areas of the curve where things can go nonlinear. Obviously, when you're looking at the background sky, you're having signal which is just a little bit higher than the noise floor. You wouldn't expect that to behave very well, and it's not unusual that you would have some nonlinear aspects as we fall off towards the noise area. So you might want to clip what data is considered in the low end so you're not sampling from areas that have poor signal. By the same token, when you look at the high end of the curve, you could have areas that are highly saturated, and once you saturate the sensor, it's no longer going to be linear. That's not good data to really try to do a linear fit from. So the idea here is you can use these sliders to come in and try to adjust that. Now I have mine adjusted from 0.1 going up to 0.85, and I came up with that as a reasonable value by clicking on these images and looking at the background sky levels and looking at the highest signal levels and try to decide where I wanted to put my thresholds. I've also run this where I haven't done this at all, just use a default value, and I still get a pretty good result. But I think that if you try to eliminate some of the highest areas of signal where you might have saturation beginning to happen, or if you can eliminate those areas of low signal where you're starting to get into deep noise, I think you're going to have a better linear fit. So we have that now. The next step is very simple. All we really have to do is drag this triangle onto the other two images that are not being used as the reference. So in this case, I'm going to take the triangle and I'm going to drag that over to my hydrogen alpha image. And we'll let that process. And you can see now that the signal level is quite a bit lower. It looks like you've lost your signal level, but it's still there. Now we're going to do the same thing with the sulfur. Okay, we now have 3 mono starless images that have a much more comparable background sky level and signal level. These should be good images to be combining. It looks like they're pretty flat and with very little information, but we'll soon be stretching and fixing that. Okay, now we can combine these images together to create our first color SHO image. And I'm going to use the channel combination tool to do that. And in fact, I've already done it. So let me just open up that image. And this is the image we ended up with. So we have the color, but we also are noticing that there's not a lot there. But as we go through the normal processing that I typically do, quickly we'll be bringing this color up where we expect it to go. And basically for this particular image, next thing I would do is go in and start adjusting it with the histogram tool and the curves tool. And as I do that, I end up with an initial narrowband image, which has too much green in it, which is pretty typical for a starting narrowband image. So we're going to go through the processing stack really quickly here, and you get an idea how this image evolves. And I'm going to do that just by going ahead by saying next. And as I do this, you can see the steps that I'm starting to use until I end up with my final image. Okay, and here's our final image. At this point, we have quite a bit of detail in both color. We have some nice gradations in the blue and cyans in this area and here. We have some nice golden areas which are associated with the Hubble palette. And we've got quite a bit of detail that's being shown in these particular areas based on the processing done. The next step, of course, is to add the stars back in. And when we do that, we'll soon end up with the final image. So the next time you're trying to combine some mono narrowband images and you're trying to figure out how you want to balance them one to another, consider using the LinearFit tool.